Hey APC kids, Campbell here. In this video, our first video on electric potential and electric potential energy, we are going to define what they are, and we're going to look at electric potential or equipotential surfaces. So just a little reminder, mechanics. When work is done by the force of gravity, for example, I'm going to take my phone and I'm going to raise it. All right, as I raise my phone from one height to another, I have to do work because the work done by the force of gravity, right, is negative when I increase the potential energy. If I let gravity do work, I'm not going to drop my phone, but if I did, right, it would come down, the work would be done by the force of gravity would be positive, and I would lose potential energy. So force of gravity does positive work when the potential energy decreases, and it does negative work when the potential energy increases. So they have opposite signs to each other. This is actually true for all conservative forces. Conservative forces are forces that are path independent. Only the final and initial states matter. So like friction, not a conservative force. So this wouldn't apply for friction. But the electric force that we studied in our last unit is a conservative force. And so when work is done by the electric field, the electric potential energy is going to decrease. And when the electric field is negative work, or we're working against it, the electric potential energy is going to increase. And that is right. It makes sense because if we treat the electric force like a gravitational force, right? The electric force, for example, if I put a positive charge here in this plate, the electric field is going to push it down towards the negative plate. And so if I let it go, that's what it's going to do, right? It's going to go to the negative plate. And so its potential energy is going to decrease while its kinetic energy increases. So we have a transformation of energy going on here. And it's always the work and the potential energy are always opposites of each other when we're talking about the work done by the electric field. So the change in electric potential energy is always opposite of the sign of work. And if you remember from mechanics, work, or the change in potential energy, is the integral of the force with respect to distance. This also applies to electric forces as well. So if we're going to take a look at a couple different scenarios here in terms of electric force. One equation we have, which works with parallel plates, it works with all things, is the electric force is the electric field times the charge that we put in the electric field, not the one that's creating the electric field. So if we put this equation in, then we get that the change in electric potential energy is the negative integral of Q, the charge that we put in the field, times E times dr. We take an integral of position from A to B. And when we do that, we just get the integral of dr is just r. And so our limits would be rb minus ra. And of course, we have a negative out here. So that's the work done with the, it wouldn't be negative if we were talking about the work done, but it is for the potential energy change. And so, if we get rid of the negative, that should be QE RA minus RB. Or we could just think of it this way, that the change in electric potential energy is Q times E times the change in position. Now, a couple interesting things about this. As I said, when the work done by the electric field is positive, the potential energy decreases. And if we move the charge in the opposite direction of the electric field or the electric force, not necessarily electric field because negative charges always move the opposite direction, then the electric potential energy increases. So this is what I want you to think of. If the charge goes in the direction, goes in the direction it wants to go. So its natural direction, if we let go, just like if I let go of a ball, it's going to fall. Wants to go then the electric potential energy is going to decrease because it's moving with the force of the electric field. So if the charge goes in the direction it wants to go, we have a decrease in the electric potential energy. Now, if we have a negative charges always, remember the electric field is set from positive to negative. So a negative charge, if we let it go, it's actually going to move in the opposite direction of the electric field. But if it moves in the direction of the electric field, then the potential energy is going to increase. So what I like to do anytime I'm like, what is happening? If I have some plates and they have an electric field vector like this, what I'll do is I'll actually draw the charges. I'll be like, oh, here are the positive charges, here are the negative charges. And so if I put a negative charge in here, what's it going to do? It's going to go in that direction naturally because the electric force is not in the same direction as the electric field vector. I know. Why does it have to be difficult? All right. Now, we also have this equation, right? Coulomb's equation for point charges for electric force. And so we can do the same thing. We can put in the electric force. We can take an integral. And of course, when we take an integral, we want to take all of our constants out, right? All these things are constants here. So we're taking the integral of 1 over r squared dr. So what is the integral of 1 over squared dr? Well, I know some of you are new to calculus, so you can think of it, I'm going to write it over here, right, as r to the negative 2 dr. Maybe that'll help you because then the integral makes more sense. So if you do that, right, the integral of that is going to be a negative 1 over r. I guess that's over here. Huh. So, and then our limits go from some point to another. So here is a test charge that we're going to move from some point A up here to some point B. And so my limits would be from RA to RB, measured from some other point charge. This is the little charge I'm moving, by the way, if you are looking at the picture. And so if I do that, right, I'm going to have, if I do that, I'm going to have that my work is equal to QQ over 4 pi E naught. And then we'd have a negative 1 over RB minus a negative or plus 1 over RA. Now, remember that these are opposites in signs. So this is the work done. But if I want the electric potential energy, then I'm going to multiply a negative through all of this because the electric potential energy and work are opposite signs. So if I multiply the negative through, then I'm going to get this equation right here. So the electric potential energy of point charges, if I have 2 point charges, is going to be QQ over 4 pi E naught and then 1 over the subtraction of 1 over the distances. Now, the 0 point for potential energy is an arbitrary thing. For gravitational potential energy, we usually set it as the lowest point in the problem, like the floor or whatever. So it's an arbitrary thing that we set. So for the same is true for electric potential energy. Electric potential energy, we need a 0 point, and so we usually choose infinity. I know you guys freak out when I say the word infinity, but significantly far enough away that the charges are not interacting with each other. So that means that the equation is going to be this. The electric potential energy is QQ over 4 pi E naught R, or, right, 1 over 4 pi E naught is the same thing as K. So we could do K QQ over R. So notice that looks a lot like the electric force equation. The only difference is it's just a single R in the denominator, not an R squared. Now, besides the fact that we have a single R in the denominator, this is the other thing. So remember when we did forces and used KQQ over R squared, the sign of the charge was not in the calculation. It was to determine the direction of the force. That is not true for energy. Energy is a scalar, so we use the signs of the charges. So if you have a positive charge and a negative charge, then one of these Q's is going to be positive and one's going to be negative. If they're both negative, then they're both going to be negative. So this is hugely important. The sign, we use the sign of the charges when we calculate potential energy. Now, if we have multiple charges, and in class on another day, we're going to go through all the different types of calculations. Because remember with force, right, we had our kqq over r squared. We had our integral of kq over r squared. We had, the electric field stuff. We had integrals, we had Gauss's law, we had all that stuff. You're going to see that again. So if we have multiple point charges, the electric potential energy is a sum of all of the electric potentials. And so you just sum them up over all the pairs. Before we do that, let's look graphically at electric potential energy. So if we have, because we use the sign of the charges, if we have like charges, so two positives, the electric potential energy is going to be positive. Two negatives, right? Negative times negative is a positive. So because of the relationship of that electric potential energy is proportional 1 over r, the farther I get away, the smaller that the electric potential energy is going to be. So we're going to see that inverse curve. If we have opposite charges, then since we use the sign of the charge, we're going to get a negative value. And so our negative value, if we were to graph it, it looks really a lot like our gravitational potential energy graph, because these are attractive forces just like masses are attractive. So we see the similar sort of thing. So let's look at how we would calculate the net electric potential stored in this arrangement of charges, which are in a square of side d apart. So in order to calculate the net electric potential, we're going to sum up all of the, and I'm just going to use k instead of 1 over 4 pi e naught, k q over r for all the combinations, and use the sign of the charges. So that means the net electric potential, electric potential energy is going to be, and let's number these, 1, 2, 3, 4. So it's going to be the combination of U1 plus 2, U1 and 2, U1 and 3, plus U1 and 4, plus U2 and 3, so let's be a U, plus U3, 2 and 4, plus U3 and 4. So those are all the ones we're going to have to calculate. Okay, so the K for all of these is the same. So I'm just going to take the K out here, and then we'll do all these. So 1 and 2, we remember use the sign of the charge. So it's plus 2Q times Q, plus Q, and its distance, that distance is just D. To that, we're going to add 1, 3. So 1, 3, we have a plus 2Q and another plus 2Q all over, and this one is going to be, this distance here, right, is root 2D. And then to that, we're going to add our 1, 4. So our 1, 4, we have the plus 2Q minus 2Q. All over, and that these are multiplied. Don't subtract those. And that's over D. And then we got our next one here, which is our 2, 3. So that's 2 pluses there. We had a plus Q times a plus 2Q all over D. Our 2, 3, we have a plus Q and a negative 2Q all over root 2D. And our last combination here is the 3, 4, which is the plus 2Q, minus 2Q, 2Q, all over D. Okay, so over here, that gives us 2Q squared over D plus 4Q squared over root 2D. Plus a negative 4Q over D. That's from this pair over here. And then plus, we have our 2Q squared over D, plus our negative 2Q squared over root 2D. And finally, plus our negative 4Q over D. Okay, Well, we need a common denominator. Do we see anything that just cancels right now? Let's simplify what we got. Let's simplify the d's and the root 2d's. Okay, so I have 2q squared over d and 2q squared over d, which is plus, sorry, that should be squared there. That would be 4q squared over d, and this is a negative 4, so okay, 4, why am I saying squared? Q squared over d. So those are gonna, that combination is gonna cancel. That's a root 2, that's a root 2, and that's not a root 2. Okay, so what we have left here, we have k, and we have, so we got rid of that. So we have this one, which is 4q squared over root 2d minus, what is happening? Minus negative 2q squared. I guess I could have simplified that while I was at it. 2d, and then minus. Now we're going to have to make the common denominator here. So I'm going to multiply both the top and the bottom by root 2. So we're going to have minus 4 root 2q over root 2d. Okay, so if I look at this, we can simplify that part right there. So that's 2q squared. So that simplifies that. Minus 4 root 2. Sorry, that was a q squared. Sorry, I lost my q squares. Q squared all over root 2d. And of course, you know, we can simplify this some more if you'd like. Or I can just leave it like that, because, you know, time is of the essence always, and, you know, the clock's ticking, right? So we could simplify. We can, oh, I forgot the k. Oops, missed the k, or 1 over 4, you know, you choose. Now, so that's how we'd go about calculating it. Isn't that fun? Lots of fun, right? Now, what about if we switch the arrangement? What if we switched, oh, my face is in the way, I apologize. What if we switched these? So see here we have q and plus 2q, and then I switch them. If we did this, do you think the electric potential energy would increase, decrease, or remain the same? So I want you to think about the amount of work it would take to move a positive 2q from here to up here. Right here, it's attracted to here, and the repulsive force it feels from this guy up in the corner is less than the attractive force here. So if I take this guy and I move him up here, so I end up with this assortment here, now this is going to be a more repulsive force, right? Because it's now the attractive force has gotten weaker and the repulsive force has gotten stronger. And this is just a little baby Q. It's half the other one, so it's really irrelevant. So it's going to take work to do that, right? It's going in a direction it does not want to go. It does not want to go up there. Comparatively more than this one. This one actually kind of wants to go down here because it's attracted to that negative charge. So that means the electric potential energy would increase in this arrangement. This came off an AP exam, wouldn't you figure? All right, so electric potential energy is the amount of energy stored in an electric field. And it's an interaction, just like forces are interactions, right? You can't apply a force to nothing. There has to be something to apply a force to. Forces are interactions. Electric potential energy is an interaction. When we talk about gravitational potential energy, it's an interaction with an object in the earth, or, you know, a mass. So remember, with forces, we also talked about fields. Fields are the alteration of space around a charged object, where if I put another charge there, it would feel a force. Well, we have the same sort of thing with electric potential energy. Electric potential energy is an interaction. Electric potential is like the potential for energy. I just have to put a charge in there for it to have electric potential energy. So electric potential symbol is delta V. And we say it is the electric potential energy per unit charge, which is really just like force and field, right? The electric field was the force per unit charge. By the way, the units of electric potential are the volts. So we frequently also call it voltage. So that means that work would equal the negative electric potential energy, which is, if we rearrange this, Q delta V. This is an equation we use quite a bit, that the work is equal to Q times the electric potential, the change in electric potential, because it's a difference. Now, we can also put in our electric potential energy equation, KQQ over R, or 1 over 4 pi E naught QQ over R, into this equation. And notice what happens is we lose a Q. Oh. And so here is the electric potential, not electric potential energy, the electric potential of a point charge. It is the potential for energy some distance away from a point charge. For continuous charge distributions, we're going to do an integral of the charge. So we're going to have to add up all the charges at some distance r. So we'll talk more about calculating electric potential in class. Just like previously, we talked about the electric potential energy in terms of the electric field, we can do the same thing about the electric potential difference. So electric potential difference between A and B is equal to the work done per unit charge to move the charge from A to B. So we just said that the electric potential, oops, that's supposed to be a V. Electric potential, looks like a U, is the change in the electric potential energy per charge. But we also know that the electric potential energy is equal to the negative of the work done. So we can say then that the electric potential is the negative of the work done from A to B divided by the unit charge, or the work per unit charge. And we know that work, right, is the integral of force with respect to distance. And we know that the electric force is equivalent to E times Q. So if I plug that in here, and you'll see that the per Q times Q cancels out, and we get that the change in voltage, or the electric potential difference, is the negative integral of the electric field with respect to distance. Now, as a general rule, when you move in the direction of the electric field, the electric potential will decrease. Right, we see this negative sign, we see this negative sign here for our electric potential. And moving against the electric field increases the electric potential. So as you move along those field lines, the relationship between the electric field and the electric potential are opposite of each other. Parallel plate capacitors are lines of constant charge, right, where we have two opposite charged plates. And because the field is uniform, instead of doing an integral of the electric field, we can just take the electric field and multiply by the separation between the plates, or wherever the charge is. So because of this, the electric potential has a linear relationship with the distance between the plates when I have a uniform electric field. Now, we always set the negative plate as the area of low potential, which means it is going to have an electric potential of 0, and then we steadily increase as we move up towards the positive plate. Now, a positive charge, if I put a positive charge in here, if this is my negative plate here, and this is my positive plate up here, we'd say that this is my area of low potential, or 0 volts, and this is my area of high potential. I don't know. I'm just going to make up a number. Let's say this is 10 volts. And so halfway in between here, right, that would be like 5 volts. If I put a positive charge in this space, right, it's going to feel a force in this direction, in the direction of the electric field. Sorry, that's supposed to be straight down. In the direction of the electric field. And so a positive charge is going to naturally move to areas of low potential. A negative charge, however, if I put a negative charge in this space, right, it's going to feel a force this direction, which is in the opposite direction of the electric field. So we say that negative charges move in the direction of areas of high potential. Now, I just want to clarify low potential versus high potential. Low potential just means it's an area by a negative charge. High area of high potential is an area by a positive charge. It has nothing to do with the magnitude of the potential, because remember that potential energy is a scalar concept. And so when we talk about scalar concepts, we talk about negatives as being low numbers and positive numbers as being higher than negative numbers. Last topic are equipotential lines, also called equipotential surfaces. Since in a uniform electric field, the electric potential increases linearly with distance, when any distance from the plate, I'm going to have a set electric potential. And so we can make lines that are called equipotential lines, and these equipotential lines are lines of constant potential. So this dashed line on the slide here is a line of constant potential. That is called an equipotential line or an equipotential surface. Just like we drew electric field diagrams, those maps of the electric field, we can do the same thing with electric potential lines or equipotential lines. We can make a graphical representation of the electric potential. Those lines are always going to be perpendicular to the electric field line. So in a uniform electric field, like this picture here, we're going to have nice, straight, equipotential lines. The reason why they're also called surfaces is because we like to think of the electric potential in terms of a surface, like a topographical map. And so a positive potential would be like a peak, and a negative potential would be like a valley. If we draw equipotential lines, those are the green ones on here, for two opposite charges. So the red picture is the electric field lines. There's a couple rules for drawing equipotential lines. Again, an equipotential line is a line or a surface where all the points have the same potential. They are always perpendicular to the electric field lines at any point. So any intersection here between these green and red lines, that's going to have to be perpendicular. The electric field always points towards areas of low potential. So, right, electric field lines always point from positive to negative. So they're always going to point towards areas of low potential because areas around negative charges are areas of low potential. And importantly, if work is equal to Q delta V, right, because delta V, that's a V, delta V is work divided by Q. If work is Q delta V, then if I move a charge along an equipotential line, there is no work done because there's no change in electric potential. Make sure you draw this diagram in your notes. This is a diagram for opposite charges. Remember that we use the sign of the charge in calculations, and I know we haven't talked about those, but directly in between two equal charges of opposite signs, this is going to be 0 volts, right? Because we're going to have a positive Q minus Q, and that's going to equal 0 when we sum up our KQ over R, so using the sign of the charge. And again, we're going to get into the calculations in class. For same sign charges, we have, I think it looks kind of like a raccoon mask or a face. The blue lines here are my electric field lines. The green lines are the equipotential lines. Notice there's no line here in the middle. There's no 0 because we're adding, when they have the same signs, we're adding together the potential from both as we go around the charges. So here's some made up numbers here. Obviously, we're going to have a higher negative number when we're closer to the line. and they're going to decrease as we go away. But we make this kind of like raccoon face, which is really kind of interesting. And by the way, there was an AP exam where they actually asked you which electric potential line which map was for like charges or opposite charges. So make sure you draw those. I know this is a super long video and I apologize for that, but I will see you in class and we'll look at how do we do calculations with these things. So I'll see you in class.